So there's a great example of what we talk about when we're talking about design, prototype, and deploy, especially the designing and prototyping of a wireless communication system. And we emphasized a lot the importance of being able to integrate and write the different types of IP that you need for the FPGA. But there's a lot more to these applications than just integrating IP. There's very high-speed, multi-rate, asynchronous signal processing going on. There's a lot of streaming of high-speed data amongst many different types of hardware devices. And so over the last couple of years in our NIWeek keynotes, some of you may have remembered that we've demoed the evolution of a tool that worked at a system level to let you build just these kind of applications in a more natural block diagram way. So here to give you the latest update on this tool that we call the LabVIEW System Designer, please welcome Mike Trimborn and Ryan Verrett. Okay, Mike, so tell us what the LabVIEW team's been working on for system design.
Yeah, so my team is working on a new tool called LabVIEW System Designer that allows users to graphically design complex systems that integrate I/O, also implement signal processing and control algorithms, and distribute their application across multiple devices and targets. And Ryan here is an internal Pioneer user for the LabVIEW System Designer and has designed a communications application that we'll be showing you this morning.
So as the NI FlexRio product manager, I'm often asked to help customers figure out how to develop their FPGA applications. So today, we've actually implemented a digital receiver which will acquire an RF signal, process it, and then display it on our high-definition television here.
Oh, hold on. I really hate to interrupt you, but are we going to see another NIWeek demo of streaming high-definition video on a TV?
That's right, Mike. We've done HD TV before, but today we're doing something a little bit different. We're actually going to show you how we built this system right here on stage.
Okay, so if you can show us how to build it, that will really be different. So what do you got?
So this system acquires an RF signal, down-converts it, demodulates it, decodes it, and then sends it out to the TV for display, all in real time. The RF signal that we're acquiring contains a modulated MPEG-2 stream, while our hardware consists of a PXI Express chassis, a PXI 5600 RF down converter, 2 FlexRio devices for the I/O and signal processing, and then a serializer module to take digital data and send it to the TV over HDMI.
So this system has 2 of our FlexRio FPGA products. Tell us what you're doing with those.
So the FlexRio architecture consists of a programmable FPGA device coupled with interchangeable I/O adapter modules. Now the adapter modules provide the application-specific I/O, analog or digital, that you require, while the FPGA module allows you to implement custom algorithms in hardware. In this system, we're using a prototype 100 megasample per second, 14-bit analog input module on the first FlexRio to digitize our intermediate frequency signal. And then on the FPGA, we're doing further down conversion and demodulation. On the second FlexRio, we implement an MPEG-2 decoder core and then send the data out to the TV through the NI6581 high-speed digital adapter module.
Great, so now that we know about our hardware for our application, let's dive into the LabVIEW System Designer to see how we can visualize and configure the hardware in our system. First, in the editor on the left-hand side, you'll notice that we have a palette that displays the hardware available to us in our system. We'll go and drag that onto the diagram, and you'll see nodes that represent our Windows PXI controller and our 2 FlexRio devices. In addition, we display hardware components that are specific to each device. So for instance, on the FlexRio, we have the 40 megahertz onboard clock and the I/O adapter module interface. And the first thing we'll do is go and assign and configure the I/O adapter module interface for the I/O adapter module that we actually have plugged into the FlexRio device. This will give us access to the digitized RF signal coming in from there. Now we need to configure a clock for that particular device. And to do that in the LabVIEW System Designer, we simply wire the appropriate clock into the clock terminal of the I/O adapter module.
Okay, so let me make sure I understand this. So today, this type of hardware discovery and configuration is all done through menus and dialog boxes and the tree of the LabVIEW project. With the LabVIEW System Designer, it's all done graphically. There's blocks on the screen and you wire the configuration. Is that right?
That's right.
Okay, so now what do I do with it?
Well, now that we've configured our hardware, it's time to start implementing our IP. Now, I've acquired a high-performance MPEG-2 decoder core from one of our partners named Amphion, who specializes in application-specific IP. I also downloaded a LabVIEW FPGA demodulator from our RF communications library on NI Labs. And finally, I know that Xilinx has the last bit of IP that I need to finish off our digital down converter.
So now what we're going to do is we're going to switch back to the LabVIEW System Designer and go to a pre-configured or partially completed system diagram that shows the clock and the I/O adapter module that we configured in the last demo, as well as an asynchronous VI for part of our digital down conversion, and then an asynchronous VI for our digital demodulation. Now we need to bring in the last piece of our IP. To bring in the Xilinx IP that Ryan had mentioned earlier, we actually have express-like blocks that allow users to configure a Xilinx IP included in their core gen library. For this application, we're going to configure a direct digital synthesis block to provide the appropriate reference signals for our application. And to communicate data, pass data from that IP block to our asynchronous VI, we simply wire that data from the IP block to the asynchronous VI. On the second FlexRIO, we'll see that we've already done the integration for the MPEG-2 core that we got from our partner Amphion. One great feature about LabVIEW and LabVIEW System Designer is that we were able to actually integrate this high performance and complex IP core in a matter of days as opposed to a matter of weeks.
Okay, so I think you're kind of making it clear that one of the key goals here, as we talked about even in the last demo, is it's really easy to bring in IP from a lot of different external sources. But you really haven't shown the audience IP developed in probably the way everybody here is going to develop. Can you write LabVIEW G code with the LabVIEW System Designer?
Well, Mike, this is the LabVIEW System Designer, so
okay.
Well, of course. So what we can do is we can actually double-click on any asynchronous VI and view the LabVIEW code behind that. Here we're looking at the LabVIEW code for the digital demodulation VI, and the System Designer provides the framework so that we can run that VI asynchronously, as well as communicate and pass data to the other asynchronous VIs in our application.
This is the exact model of computation that we need for our application, which has several different data rates. For instance, the adapter module produces data at about 100 megasamples per second, while our down converter produces data at 25 megasamples per second, and the demodulator at about 5 megabytes per second.